Hello, can you hear me?
Yes.
Okay, so this is now the start of the Packet Video Workshop. My name is Igor Kurcho from Nokia Technologies. Welcome everyone. This is the a special year for Packet Video. It is the 25th anniversary, and so it's a big year for the Packet Video. So many years of workshops. Next year there will be an official celebration in Istanbul. For Packet Video for this year, we have a general chair in our organization, Hermann Hellwagner from Alpen Adria Universitat Klagenfurt. Then Yao Liu is Binghamton University from the US, and then myself from Nokia Technologies, Finland. This year in Packet Video, we have we had a technical program committee a group of 21 people, 21 members, and then the paper's acceptance rate was 43%. We have organized the program with two sessions. We have one session on video streaming and coding. We had several submissions, quite good papers on video streaming and coding. I will go through very fast. One paper on HTTP2, one paper on HEVC on 360 video. We have one paper again on 360 video and tiled streaming. Then another paper on VVC, which is the emerging video codec. And then we had a couple of more papers on cloud gaming. That's why we also decided to have a second session, a separate session on cloud gaming. Okay, so this is an overview of the program for this year. I'll just go back and then give the word to Yao for the first session on video streaming and coding.
Thank you, Igor. Let me mute my. Okay. So in the first session, we're going to have 4 papers, both on the topic of video streaming. Some of them are on traditional adaptive video streaming. Some of them are related to immersive video streaming. So the first one will be presented by Mingwen, who is currently a PhD student. So Mingwen, are you able to be unmuted?
Hello. Thank you for the presentation. My name is Bing Nguyen, and my paper is about H2BR and HTTP2 based retransmission technique to improve the QoE of adaptive video streaming. The motivation behind this paper is that some adaptive video streaming, some adaptive bitrate algorithms choose the lowest quality segments in the startup phase to decrease the startup times. However, this can annoy users as they have to watch a low quality videos initially. And the second motivation is that there are some quality switches in a streaming session because of the throughput fluctuations. So in this paper, we propose an efficient retransmission technique, namely H2BR, to replace low quality segments being stored in the buffer with higher quality versions by using features of HTTP2, including stream priority, stream stream termination, and server push. So I think that's all for my introduction to the paper. I think now we can move to the Slido.
Thank you, Mingwen. Thank you, Mingwen. So looks like the Slido questions are ready. So let me share my screen. I'm having a little difficulty over here. So I will first read out the questions over here, and I will try to fix the problem later, maybe. So the question is, instead of retransmission, couldn't we have an adaptation logic that optimizes QoE and quality of variations by considering the bitrate of the next segment as well as one in the buffer?
Actually, yes, we can propose a new adaptation logic, but however, adding an extension like our paper H2BR may be easier than creating a new adaptation logic, which needs a new algorithm to choose the next segments and a new algorithm to consider the segments in the buffer. So I think, yeah, it will to have a new algorithm will be harder than this. So as first, we propose this paper for an extension to existing ABR, which can be easier.
So I think that's all the questions we have for the first paper. Let's thank our speaker. So I think next we can move on to our second paper about the encoding of 360-degree video streaming. Looks like we cannot reach the speaker for the second paper yet. Let's first move on to the third paper and see what we have about immersive tiled video streaming as well. So the third paper will be presented by Sabah Ahsan. She's a researcher at Nokia. Previously, she has been working in area of adaptive video streaming, and recently she has started working in area of immersive streaming as well. So Sabah, could you please give us a 1-minute overview of this paper?
Yes, hi, can you hear me?
Yes, I can hear you very well. Yeah.
Okay, so in the paper, we present our work on developing an ABR technique that uses existing 2D ABR algorithms for streaming 360-degree OMAF video. So we use the public sourced Nokia OMAF player for our work, and the challenge we faced was that when you're trying to stream 360 video with tiled video, with each tile has different level of complexity, and if there are different sizes, and with the constant head motion, it is hard to predict what will be the required bit rate for a particular quality in the viewport, especially because we were trying to keep the buffer very short so that we don't end up wasting any bandwidth. So we developed a technique which we call Frisbee, full sphere bitrate estimation, and with this technique, which we implemented on the Nokia public sourced OMAF player, we were able to minimize stalls to almost zero, despite some changes in the network bitrate, and using an extremely short 3-second buffer.
Thank you, Sabah. So there's a question on Slido. So the question is, what are the main challenges in bitrate estimation for 360 degree with respect to classical video, or I guess traditional video?
So the challenges that we faced was that we encoded the video to have different tile sizes for better coding efficiency. So we had larger tiles in the equator, and we had smaller tiles in the polar regions. And then we also because the tiles have different complexity, the amount of bitrate for each tile was different. So in the manifest, you only get the bitrate for each tile for each quality. And as you move your head, depending on the tiles that are in the viewport, the required bitrate can be drastically different. And when we checked for some of the videos that we encoded, we were able to see that the change could be as much as 30 or 40% bitrate variations. And this, when you keep an extremely short buffer in order to minimize wastage, this results in stall events. And so we developed this technique to minimize these stall events.
So the second question is a follow-up question. Will the answer to the previous question regarding bitrate estimation be different for CubeMap video?
I think not. So I am not the expert who dealt with. I'm not the author that that dealt with the projection in the paper. But I would think that it should apply to both. So. But I can answer this question on Slido, the detailed answer on Slido after consulting with my co-authors as well.
Thank you, Sabah. So it looks like we have finished the 3 papers. The fourth paper is also a paper that's related to the new type of video in the context of versatile video coding. So this is also a paper by Nokia Technologies.
Hello, do you hear me?
Yes, please.
Yeah,
yes.
This is Alireza Aminlu from Nokia. Yeah.
So could you please give us a 1-minute overview of this work?
Yeah, this work is about a new coding tool in VVC, versatile video coding, which is called affine motion compensation. Affine motion compensation is to predict when there is rotation in object. But the study that we did is that when there is a big rotation, the current affine motion compensation in the standard is not able to handle it. So when I say big rotation, I mean kind of 90 degree or 180 degree or flipping, this kind of rotation. And we noticed that this kind of rotations happen in this point cloud content. There is this video-based point cloud compression method. There we may have big rotation in different frames. So different patches, which is a concept of PCC, may be packed in different frames with different rotations. So we tested our method in this PCC use case where there is this kind of big rotation or flippings, and we were able to achieve kind of big gain, in average 3% bitrate reduction, and in the maximum 6% bitrate reduction in one of this point cloud test sequences. Yeah, this is short introduction.
Thank you for the introduction. So looks like we have a question over here on Slido. The question says, have you studied the effects of the proposed method on VCC's CTC sequences?
Let me read the question again. It doesn't mention that the case in VPCC. The VPCC is just the use case. So this tool is suggested for VVC but the use case is PCC. So we didn't put PCC in the, so we are not here claiming that we have a good coding tool for PCC. We are just trying to fix or improve the functionality of a function in VVC, in versatile video coding. This is why we put this VVC as in the title. Yeah, PCC is just a use case.
So let me clarify. Does that mean like the proposal method can be used for other use cases other than VPCC as well?
So the field of the no, we haven't. Yeah, we studied this method in VVC, the common test condition. There we didn't have any gain because we don't have any big rotation in those content. So we selected PCC because we have big rotation there. So yeah, we just tested in these two cases, not other cases.
That makes a lot of sense. Thank you.
Yeah, and before finishing this, I'm also responsible to present the second paper. So when this finish, I can come back to that second paper.
Sure. I think we can finish. We can wrap up with paper 4 and go back to paper 2 right now.
Yeah.
Okay. Yeah. Sure. Could you please also give us a 1-minute overview of paper 2, please?
Yeah. This second paper, when we have this VR streaming, usually we have a big resolution in 360 videos, like there are 6K and 8K. But usually we stream lower resolution because decoder on the mobile devices are able to handle only 4K video decoding. So we need to fit 6K or 8K video into 4K video. So we use this adaptive viewport adaptive streaming, where the viewport where the user is watching, we stream that area in higher quality, but the rest of the area which user is not watching in the lower quality. So we downsample some part of the video and pack 6K or 8K video into 4K. So we have two different packing for ERP and CMP, I mean cube map projection. So in this study, we compared that if we stream this ERP or CMP with that constraint of 4K resolution, then which one, I mean ERP or CMP, which one gives the better quality at the receiver side? So we use a specific type of test methodology, which is very important in 360, as discussed in the opening discussion, that we use a specific test methodology, and we showed that using ERP or CMP is very content dependent, but in average, they shows the same RD performance. So using ERP or CMP with those specific packing doesn't matter. However, it is very content dependent.
Thank you. So there was one question on Slido that asks, it's a very simple question, asks, how much are the rate distortion results content dependent?
Yeah, I think I already answered that question. It's very content dependent. As you see in the paper, there are big variation between different contents, but in average, they show almost the same performance. So maybe one good study can be in the future that to analyze why CMP and ERP showing different performance in different content. It's really content dependent.
Thank you. So that concludes the first session on video streaming at the PV workshop. So next I'm gonna let Igor to start the second session on video gaming.
Okay, thank you. So the second session includes 2 papers. It's about the cloud gaming. And the first paper is SARA SDN, State-Aware Resource Allocation in SDN to Improve QoE in Cloud Gaming. We have 3 authors from the University of Tehran, Iran, and I would like to invite the speaker to give his pitch, please. Do we have the author of the first paper? Not yet.
Hello.
I think
Yes.
the author
hear
is
me?
here. Just need to be unmuted.
Yes.
Please unmute Mr. Farhad Pakdaman. Do you hear me?
Yes. Yes. Okay.
Yeah.
Please.
Thank you.
Hello, everyone. Hello, Igor. Sorry for the confusion. I will be presenting both our papers here.
Yes.
So I hope that's okay. Okay.
Yes. So please go with the first one.
Okay, sure. So our first paper, Sarah SDN, is a state-aware resource allocation in SDN for improving the quality of experience in cloud gaming. So we know that in cloud gaming, we have some kind of a game as a service. So the game is being played on a server somewhere, and the video of the game is sent to the audience, to the player, and player communicates with that game. So one big challenge in this paradigm is the delay between the cloud server and the player. And to handle that, we propose to have an SDN architecture that takes into account the state of the game, as we noticed that the game, even inside one game session, we can have different states of the game. Like there are demo sessions which the delay can be really tolerated by the player, and we have like combat scenes that you are very much engaged with the game, and even a little bit of delay can be observed by the player. So we propose an architecture that takes into account this state of the game and uses an SDN architecture to optimize the delay for all the players.
Okay, thank you. We have some questions here. I'll display these questions.
Sure.
Let's see. They're here. Yes. So is it a feasible assumption to know that game state information, network metrics information, etc., is this usually available?
Well, of course, the network metrics are available in an SDN paradigm, not in everyday networks, in all networks. Of course, you can have some metrics, some parameters to describe the state of the network. But in an SDN architecture, we have these kind of network. The SDN controller can demand this information from the servers and all the network devices. So that's this part of the parameters. As for the game state information, actually, we need to do something to have that. By default, you don't have that kind of information. One way that you can obtain this kind of information is to embed some kind of code into the game engine. That's what we did. We had open source games for our test environments, and we have some kind of code in the game engine that can tell you the state of the game. This is one way to do that. And I believe there are more ways to do that. Even I think that we should be able to train a network, train some kind of model to tell us based on the game scenes. So yes, by default, we don't have that information, but we should work to get that information, and there are ways to do that.
Okay, thank you. Your paper is quite popular because you got many questions. The next one is during taking the allocations decisions, what is the impact of SDN on latency? Also, did you analyze the scalability of the proposed system? For example, tens of thousands of gamers?
No, actually, we didn't do that because it takes a lot of time to simulate that kind of network. And for this particular paper, I think what's the most important is that we are kind of analyzing the quality of experience. So we were really interested in implementing this system in a real-time system. So it was actually 2 servers inside our lab, and the players could sit here and actually experience everything. So it was impossible to simulate it for thousands of gamers. But I think what we did in the other paper, which has actually a more complex algorithm shows that we can have thousands of gamers, or at least hundreds of gamers. That's what we tested in that other paper, and it was okay. So I think it's going to be a scalable. I think I didn't answer the first part of the question. During taking the allocation decision, what's the impact of SDN on latency? I don't think it has any kind of impact on that, or at least I can't think of any scenario that the SDN would have anything on the latency, unless you're referring to the added overhead that we are adding to the centralized node.
Okay, thank you.
I hope I answered the question.
Yes. What is considered as a state, and how did you determine the bandwidth and delay requirements for each game,
Yes. Well, the state is actually kind of a vague terminology used here. And the state of the game can be implied by many things. One of the most important thing is the state within the game that you are playing. Like as an example, it can be the demo sessions. So when you are in the demo session, you have different requirements. Or different bandwidth requirements. When you're watching the demo session is some kind of a pre-recorded video. So you are just watching a video. So the quality of the scene, the PSNR might be more important to you than the delay, because you won't feel the delay, you're not interacting. While in the other states, like in playing or a combat scenario, you might not be even able to look at the entire scene. So we might be able to even reduce the bandwidth allocated to your game, and you won't even notice that, but you are very sensitive to the delay that you're perceiving. So I hope that clarifies what the state means.
Why there wasn't any other traffic in the framework? For example, data, video streams, etc.
I think I answered that in the first question, as we were focusing on implementing the system as some kind of a real time, so that the players can actually sit here and experience the game. And we didn't use simulations, pure network simulations. We didn't consider any other data, video, or other streams.
Okay, thank you. The last one, what is the meta reasoner to make decisions about paths? Can it be done in real time?
Can it be done in real time? I think so, and that depends on how often this algorithm runs in the SDN controller. And the answer would be that we run the solution every time the network states change, a major change in the network, or the state of a game change, and the game server sends those as some kind of signal to the SDN controller. And it doesn't run all the time, like every half a second. So yes, it can be done in real time, I think. But of course, that would add some kind of latency and some kind of extra computation to the SDN server. Sure.
All right. Thank you very much for this paper. We have now the last paper of this session, which is a Frame SDN, a fair resource allocation for multiplayer edge-based cloud gaming in SDN. We have, again, authors from University of Tehran, Iran, and basically it's, again, you presenting this paper.
Okay, so this second paper actually kind of completes that first paper, I think. The challenges are the same. We have cloud gaming, and delay is, I think, the most challenging part of the cloud gaming. But here we are actually extending that to multiplayer gaming. When you are playing with multiple players, one extra challenge is that you should have similar delays to each other. If you have a better delay or worse delay than your friends, you might have an advantage over the game. So what we work on this paper is to provide a fair situation delay-wise for all the players, so that they can have a fair game. Again, we use the SDN because we want to have a central overview of the network and know all the requirements of all the players. And we formulate and solve this problem as an optimization problem using a genetic algorithm. And we show that it outperforms the existing solutions.
Okay, thank you. You have got 3 questions on this paper. The first one is, does the optimization problem depend on the actual interaction of the players? i.e. their behaviors?
Mhm. I think in practice it might, in a very minor way, it might actually depend on the interaction between the players. Like when you are walking down some path in some kind of combat game and you're not actually shooting your opponent, you might not need to have the same delay. But when you are in a different state, when you are in a different scenario, it might actually be more important. But it doesn't have a major effect, I suppose, and we didn't consider that. What it depends more is that in general, we think that they should have a similar environment. So we try to optimize the interplayer delay. That's the difference between delay of different players at all the times.
Okay, thank you. Did you consider any NTP server to provide synchronization between clients and server? Can you elaborate on how you provide such synchronization considering the SDN overhead?
Mm-hmm. I have no idea about the NTP server, to be honest, and I don't know how we would use that, but we are abstracting that part, I guess, as the details of the network implementation. What we consider is that we have two types of servers, the cloud servers and the edge servers, and the cloud server is responsible for the synchronization between the clients and the server. So I hope that answers the question.
Yes, in a short way, yes.
In a short way, I guess.
Last question. I think online gaming servers are responsible for synchronization and multiplying, not cloud gaming servers. Have you considered the online gaming servers and what is the role of the lag compensations, such as lag on your method?
Multiplying the cloud gaming. I think that's saying multiplying actually, but it was a typo. So, so let me read the question again. It wasn't clear the first time. I think we are talking about the same thing, like cloud server and the cloud gaming server. So again, referring to the answer to the last question, we have two types of servers. The first one is responsible only for the synchronizations and having the overall logic of the game. That's a cloud server. And then we have edge servers, which are just responsible for rendering the game and encoding the video. So yes, this is the type of server that we have considered.
Okay, thank you very much for your answers.
Thank you, it was my pleasure.
And this is ending the Pocket Video session.